Hi everyone, my name is Stephen Wu and I'm an associate professor at UTHealth. My field is natural language processing in EHRs, and I'm currently working remotely most of the time from North Africa. Today we're going to be talking about deep learning in clinical natural language processing, and we're going to do it in a few different steps. The last step will be actually a literature review or a systematic review that we have just completed here at UT Health. So you'll get to see some exciting things. Now, historically, deep learning, which is a really exciting field, historically, it comes from neural networks. And so we're going to start out by giving some background on neural networks. Neural networks were originally part of just normal machine learning, what we'd consider statistical or whatever other kind of machine learning. And the early definition by Tom Mitchell back in the 90s was this: neural networks are built out of a densely interconnected set of simple units where each unit takes a number of real valued inputs and produces a single real valued output. Now, that definition is a little bit outdated now, but you can see that neural networks have been around for quite a while. Now, neural networks actually did a really good job at the tasks that they were applied on. There was good performance. However, there was very poor explainability. People couldn't figure out why these black boxes of neural networks were working. And so what ended up happening was that neural networks fell out of favor with most researchers because of the lack of explainability. Now, there were a few people who continued to use neural networks, and like Jan LeCun, Joshua Bengio, Hinton, and these folks continued to press on with neural network research until in 2012 and 2013, neural networks became repopularized as deep learning with a few new improved techniques. One of the things that instigated this sort of revival was the ImageNet competition in 2012. There's a 1.2 million high-resolution training images, and you're trying to figure out which of 1,000 classes each of those images belongs to. So it's a very highly multi-class classification problem for these images, and you just need to predict the correct label in your top 5 guesses. Now, when you looked at the systems that participated in this, the deep learning algorithm actually dominated the competition. You can see here that all of the other groups their error rates were much higher. The gap here for error rates was huge. And so what ended up happening was that deep learning started to get a reputation for just working, for being empirically just great results. And this kind of improved image recognition and labeling is exactly what allowed, back in the day there were Facebook face tagging in photos, and it was very poor in performance. It drastically improved in performance because of this deep learning. And so the face recognition that we have in all the social media platforms, Instagram, whatever else, is deep learning these days. Deep learning is now the de facto standard, not just in social networks and things like that, but also for computational research. Anything that used to use any other kind of machine learning, like speech, vision, natural language processing, any kind of artificial intelligence, anything that used to use ML now uses deep learning as an improved kind of machine learning. And if you are not using deep learning, you have to basically at least compare with it because everybody else is using it. Deep learning does get art results on many tasks. I'm not even going to list them here because it's always changing, but many tasks in all of these fields that I've mentioned get state-of-the results with deep learning. One of the most appealing things about deep learning is its simplicity. There's no need for feature engineering. As the technical person, you don't have to go in there and figuring out what are the patterns in the data that I want to draw out of there. Instead, you're just feeding in data and you're letting the system itself figure out the patterns in the data. So today what we're going to do is we're going to look at some neural network basics, the old school neural networks, and get into back propagation and stuff like that. Then we're going to look at deep learning architectures for natural language processing. And I'll give you a map of architectures. And then we're going to talk about the literature or the systematic review or methodical review, where we look at what is being published and what is being done in clinical NLP with respect to natural language processing, or with respect to deep learning. Okay, so let's look at some basics on neural networks. When you're thinking about neural networks, you have some quantitative inputs, like pixels, or if you can represent words as numbers, which we'll talk about later. But your inputs are some kind of quantitative input, and then you have outputs. Now these inputs here, what you want to do is say, how relevant is this input to my outputs? And so if you're going to calculate here with, for the output 1, how am I going to say what is the quantitative value for this output? And how likely is it compared to output number 2? You want to weigh the things in your inputs and figure out which 0, 1, or O1 or O2 is more likely. Now the way that you figure out the differentiate between O1 and O2 is by means of these weights. So these weights are coefficients for each of the inputs, and the lines are representing those weights. And these are basically give you a linear combination of your inputs to produce some kind of an output. Now, for a neural network, it's not quite a neural network when you've done this. This is just a linear combination. You could do it with linear algebra. Neural networks usually have a nonlinear layer, which after this output is produced, that output is then fed into, as input, into another layer, a nonlinear layer, something like a hyperbolic tangent or sigmoid or something like that. And so you have the inputs here being passed through a tanh to the outputs. Now, the first generation of neural networks were perceptrons, and you had input units, and they went to multiple features in a middle layer, and then to output units. But the middle layer here in this first generation was non-adaptive, hand-coded features. And so it was not dynamic. It couldn't figure out. You'd have to go in and figure out the patterns in the data yourself and code how likely it was that you were going to weight different parts of the input for those hand-coded features. That's what the learning was doing. So the second generation of neural networks improved on this a little bit. You had your input vector going through a number of hidden layers to produce your outputs. And so these hidden layers were no longer manually hand-coded features. They were just numbers that were allowed to float, and you were training the weights that produce these values. And what you did was you multiplied things from your input vector, and you got the weights, multiplied through the weights, got the value at the hidden layer, multiplied through some more weights, and once you got your correct answer, you would compare with the output, and then you'd send the error signal. Here's the error signal. Epsilon is the difference between the real thing and the system-produced y prime. You look at that difference and propagate that error signal back through using derivatives to learn what the weights should be in this network. And so this was the neural networks that were in use for a long period of time. Now, in order to train these neural networks, we used gradient descent. Sorry, it's misspelled there. It should be a SCENT. And gradient descent, if you think about gradient descent, then it's really a, if you think about a curve, then let me draw that. You think about a curve, and you are trying to find the minimum in this curve, for example. And if you're at this point, you need to know whether you go to the left or whether you go to the right. And how do you know whether to go to the left or to the right? You know which way to go by looking at the slope of this at this point, slope of the curve at this point. And if you know the slope, then you know that this way is going down and this way is going up. Now, unfortunately, for us, when we're training neural networks, we're not looking at just one image or one text sample. You're looking at a whole data set of text samples. And so you can't so quickly say, okay, I'm definitely going left or right after I've seen one point. So what gradient descent does is it sums up the gradient for each data point, and then that's your gradient overall. And then you change your parameters, your weights. These thetas in all of these here are the parameter of the weights, the weight matrix, the W's in the previous screen. And by some learning parameter lambda, you'd multiply that to say, okay, this is how I'm modifying my weights in order to get a new value. Okay, so training neural networks uses gradient descent. More efficient is a better algorithm is stochastic gradient descent for the data set. Instead of looking at every single data point at once and then making one big update, here you are looking through each sample from the data and looking at the gradient from that and then making your updates as you go on each of the samples. Now, once you are talking about gradients, what do you put into the gradients? If you have the ability to make the gradients, how are you using those? Well, you start by, you take your input, you pass it through those weights as we were talking about, pass it through this nonlinear layer, pass it through these weights, and say you get values like 2.0 at this output 1 and 1.0 at this output 2. This is forward propagation. You're propagating the inputs through the weights and everything else to get your outputs, values at the outputs. Okay, so you're propagating those things, and now you want to figure out for this 2.0 and 1.0, okay, well, is this output 1 more likely or is this output 2 more likely? And can we talk about those in terms of probabilities? And so the softmax function will turn those scores that we had, the 2.0 and the 1.0, into probabilities. And this is the softmax function right here. It uses these exponentials, and this is the sum of all of the exponentials of all of the possibilities on the bottom here. And so what you have now is this for class 1, or so for this output 1 or class 1, you have a probability using this softmax function, and you have a probability for the output 2 from the softmax as well. Now, once you have a probability, you can stick the probability into this equation here. And this guy right here is that same probability that we were just looking at. If you take the log of that probability, it doesn't change where the maximum or minimum is if you take the log. And so we're going to maximize the log likelihood of that thing. And when we do the log likelihood of it, of that probability with respect to these weight parameters. When we take the log of this thing, we get some nice properties because we were using a softmax function and it had these exponents. Exponents and logs are inverse relationships, so you can simplify this top part to be here by just canceling out the inverse relationships and remembering that when you take the log of a denominator, it's just a negative of that same log, not as a denominator, right? So you maximize this log likelihood for this value. Now, if you do a little more tweaking, instead of maximizing this likelihood, the probability or whatever, likelihood, it's the same as minimizing a cost function. So we can call a cost function to be the negative of that likelihood, and then we can do a minimization problem on the negative of the likelihood. So that's our cost function instead. So in order to calculate that, now this is where we start to use our gradients. And if you look at for the value in the output layer to choose the ith class, or it's like O1 or O2, if that gradient is actually going to simplify to this really simple expression where you have basically a sigmoid-like thing minus 1. And for the cases where it is not the correct class, there's nothing there. So it's very intuitive when you actually look at this part here. The gradients for each output node, basically you're going to say, well, if I got it right, then I subtract the 1 from it, and then that's my gradient, negative 0.27, and then here's my gradient for the second class, or O2, C2. And so if you see that, so you can see that value here, negative 0.27 and positive 0.27 as the respective gradients. Now that I have my gradients at these output nodes, I need to back propagate these gradients back through the network so that I can update the weights at each one of these links here, each one of these links here. Every parameter, each one of these weights is a parameter, and it needs to be updated by the back propagation. Okay, so the back propagation in this linear layer, if you remember the original equation that we had here for the output was like so. There's just this linear combination of weight coefficients times inputs, z, or these are hidden layer inputs, but they're still inputs. And so in order to get the delta for the weights, it turns out to be, you use the derivative here, and it turns out to be just the gradient here at the output node times the value at z1, at that hidden node, right? So it actually turns out to be very simple. You just multiply that thing by the weight to get the change in the weight, or the gradient in the weight here. And then beyond the weight, how do you get to that? How do you get to that node so that you can continue to propagate down? The gradient at this z1 is, again, very simply, you just take the value that was here, this negative 0.27, that was the gradient at O1, and you multiply it by the corresponding weight. You take the value at O2 of the gradient and multiply it by that corresponding weight, and that's how you get the gradient here at z1. So it's a very nice thing, and it looks exactly like forward propagation, but it's just going in the opposite direction. This is why we call it back propagation. When we get to a nonlinear layer, if you recall, we were so we just did this layer backpropagating. Now we need to backpropagate down into this tan H layer. And in order to do this nonlinear projection, you just need to remember the property that the derivative of a tan H hyperbolic tangent is 1 minus that hyperbolic tangent squared. And once you do that, it's, again, very simple. You just multiply the number up here, the gradient up here, by the derivative, which does turn out to be just this 1 minus tan h squared x number. We can say that there are some drawbacks of these traditional neural network strategies. Backpropagation was too slow. And when you did backpropagation, you had the gradients here, and when you pushed them back through backpropagation, the error would kind of vanish. Like the effect of this part would get lost as you went through multiple layers of multi-layer perceptron, or feed-forward neural network. And another problem is that in traditional neural networks, you get stuck in local optima, and that was seen as a problem. Now, in more recent deep learning, we have basically tackled all of these problems, these three problems: backpropagation being slow, error vanishing, the local optima. The first one has been taken care of with parallel computing. You use much more powerful computers, and then you use parallel computing to do matrix operations, because all of these, all the linear layers, these are matrix multiplications, things like that, and those can be done very efficiently on graphics processing units, since those are used to processing pixels that are grids that can be multiplied by each other. And so GPUs are actually great for this kind of computing. More recently, tensor processing units have been introduced by Google, specifically for deep learning kinds of computing. There are other alternative hardwares, I think, that are being explored to optimize deep learning, because the techniques have been shown to be so empirically beneficial. So it does cost a decent amount to train these things. There are real-life financial costs. There's also even environmental impact of training these kinds of models. But people do it nowadays. And you can do it on a GPU for relatively cheap. It's not going to completely break the bank to invest in doing deep learning a little more quickly. Another thing that had been a problem was error vanishing. And now the observation here is that instead of doing backpropagation and training everything all at once, you can do layer-wise training. So you can train each layer and represent things at each layer, and then after you train things at each layer, you have a stack, and when you actually do your backpropagation, you are viewing each of these things as a sort of a unit. And so on the left side here, you have your feature training, where you start by layer-wise training the features, these intermediate representations. And then on the right side here, you have weight training, where you optimize the weights between these different layers. So that's one way to take care of error vanishing. And then that problem of local maximum, you could get stuck in a local maximum. And the idea with deep learning is, so what? The real world is just really complex. In conventional machine learning, what we did was we simplified models, we made assumptions, and then we tried to solve a global maximum. Well, in deep learning, we're just going to say, well, the real world is complex, and it's really hard to solve, so let's just use this local maximum. And in fact, there have been studies that show, it doesn't really make that much of a difference if you use the weights and the performance of a system that is in a local maximum versus in a global maximum. So we're just not really going to care that if we're stuck in a local maximum. There are other things that have been innovated in terms of deep learning that have made deep learning really successful in um, in recent years. Some of those are optimization techniques, so finding the gradient more efficiently than the stochastic gradient descent that we looked at. So there's different optimizers that you can use with any of the modern packages in deep learning. And I'll talk about the packages again later when we do the systematic review. Then there is the idea of dropout. And for each training sample, you delete a hidden node with some random probability. The default is often like 0.5 probability. You just delete the hidden node. And what that does is it keeps it from overfitting and from co-adapting, making things fit too closely to the data. So dropout actually improves performance quite a bit. Other things, people have introduced new neurons besides the sigmoid, like ReLUs, rectified linear units, or the softmax neurons. And people have come up with architectures for deep learning and for neural networks that actually work on real tasks. Convolutional neural networks, the recurrent neural networks based on the LSTM, long short-term memory cell, or the gated recurrent unit cell. More recently, the transformer attention-based architecture. So there are these architectures, which we're about to cover, that have been really empirically successful. And so that has really led to the adoption of this stuff. Now, deep learning is not perfect. It's hard to get academic-like proofs for anything. Hard to prove why things work, but Jan LeCun, definitely sort of a pragmatist here, is saying if we only study models for which we can prove things, we wouldn't have speech, handwriting, and visual object recognition systems today. So stuff wouldn't work. So there are limitations to deep learning, and in fact, we do think that there should be more research and analysis into the limitations. But we are looking at deep learning because it has been very successful, and we believe it will continue to be very useful in a lot of fields, in NLP and in medical informatics. Now, what do modern NLP-related deep learning architectures look like? We're going to take a big picture view of deep learning architectures for NLP today. We're going to look at pictorially how do these different architectures look graphically. So let's start by comparing with some of the traditional models that have been used in neural networks for a long time. So, and not just neural networks, but in machine learning. Logistic regression is a very common model. It's like the model that we studied at the beginning of this with the neural networks, except that there's no non-linearity. It's just you combine things linearly, but logistic regression, you're taking the log of those things. So you're combining multiple inputs and predicting something from them. That's what the inputs here are triangles, and the output is a square. You're combining these with some weights, and you're predicting that. Okay. Now, in natural language processing, during 2013, the word-to-vec model was introduced, and it's basically the same structure. It's just that here in each of these inputs, you had the neighborhood words of a particular word of interest. So if you had deep learning architectures for NLP and you were trying to focus on the word architectures, then the architectures word would be up here, and deep learning for NLP, these words would be input down here. And the idea is, can you train your weights to predict the architecture word from deep learning for NLP, from the surrounding words, okay, without actually seeing the word architectures down here. And so that's when you train your weights to do something like that. These weights can end up becoming a vectorial representation of each word. I won't go into details, but that's the idea here. Word2Vec is trying to produce a vector for each word. You're turning words into vectors. Now, a slightly more complicated version of Word2Vec is fast text. People started to realize that with Word2Vec, you were only able to represent concrete words that were already in a dictionary, and you couldn't do anything like make use of the fact that some words were related, like high versus highness. Those two words are related to each other. The concepts are related, but they're completely separate from each other in Word2Vec. Fast texts basically you take each word and you break it up into its character strings and n-grams of the characters. So 2, 3, 4, 5 character strings from each word. And so this word will get broken up into its components, that one into its components, that one into its components. And those would be included in the things that you're trying to estimate. You get weights for these subwords as well. So that's what fast text did in order to get a subword kind of model. People also looked at Word2Vec and said, gee, I have a representation, a vectorial representation, quantitative representation for words. It'd be nice if I had something like that for something bigger too, like sentences, documents, stuff like that. And so Doc2Vec sought to answer that problem by just representing the whole document as another, almost another dictionary item. The whole document together would get its own thing, and it would be trained simultaneously with these words. It had needed a few little differences with the inference time. You had to do a little bit things different, but basically these are representation learning strategies. How do you represent texts? Okay, now this kind of work actually did continue, but more so in language modeling, which we'll get to in a minute. But okay, so that was one thing. You take logistic regression, you move forward from there into modern deep learning, and you get these word representation type strategies. You also, if we look back to the traditional model of the feed-forward neural network, or the multi-layer perceptron that we looked at earlier today, with these multiple hidden layers that are a little bit hard to interpret, but had pretty good performance. This feed-forward neural network, modern day people are using these similar kinds of things to do classification, specifically text classification. Convolutional neural networks, or CNNs, are used in image processing as well, but they've also been applied very successfully to text processing, namely text classification. So you get a whole chunk of text, and this unit here, this little box with the little thing there, is like a patch. It's the convolutional kernel, and so you're saying, hey, I'm going to look at these few words together and see if they form some certain kinds of patterns. And so this is almost your equivalent, if you're familiar in the past with language modeling and bigrams, trigrams, things like that. It's getting at that same kind of intuition. You have a patch of words that are together, and that means something. So, what you're sliding a window across these words, and then you have to, once you are sliding those things across the words, you have to bring them together somehow with some pooling these convolutions and pooling. And then you pass it through another hidden layer, like just your regular feed-forward layer, and then you get your outputs. So what this does, instead of your original feed-forward neural networks, is that it basically allows your input to be much more flexible. For example, if these were images, it takes care of things like translation. If your picture was in the bottom right if a face was in the bottom right of the picture instead of the top left, this would take care of that. Lots of those kinds of problems. So similarly, in text, if you had the same phrase at the end of a sentence as at the beginning, the same noun phrase at the end of a sentence as the beginning, it would be able to pick up something like that. Oh, this is a noun phrase structure. That's the kind of the intuition here. And if that noun phrase structure is relevant for classifying this text as relevant to adverse drug events or something, then okay, great. This is a classification kind of thing. Okay. Now, another model that was introduced long ago was the recurrent neural network, RNN. And this is what we call the vanilla RNN, basically a very uncomplicated thing where you have inputs, they're going to a hidden layer, but each hidden layer is not only dependent on the input, it's also dependent on the previous hidden layer. And so this one is dependent on the previous one. So you have the vanilla RNN kind of passing information from step to step, from word to word, if each of these things are words, or from character to character, if each of these things are characters, however you want to define those kinds of things. But there were some problems with the RNNs of old. You kind of like lost information as you continued to pass things along these hidden layers. And so the LSTM was introduced. The LSTM stands for long short-term memory. And so you have a different kind of unit where it's the same structure. You're passing something from this step to the next step, and combined with the input, you do some changes, you do some computations in here, and then you predict some output, and you pass stuff onto the forward step. But inside this unit, it's much more complicated than a vanilla RNN. Inside the unit, you actually have things like a memory line. So that's why it's called a memory cell here. You have a memory portion of this unit, and it's passing the memory forward. There's a forget gate that says how likely is it that I should forget the information that I have just received. There's lots of input gate, output gate, stuff like that. So there's a bunch of components inside of this thing, and LSTMs were able to capture long-range dependencies between inputs from a long time in the past much better than these vanilla RNNs could, because it had that memory being propagated forward. There's other things in the space of RNNs that also works pretty well, like gated recurrent units, but I'm not going to cover that. In practice, what you normally see for these LSTMs is not just LSTMs. You actually see bi-LSTMs, where not only are you propagating things forward in your recurrent neural network, you're actually also running the same kinds of computations backwards. So this whole yellow part is backwards computations of the same thing. Now, there's also a newer word representation strategy called ELMO, which is pretty similar, but the reverse direction is trained basically separately from the forward direction. And so the idea with ELMO is not so much to model the whole language, the whole sentence, or the whole sequence of words here, as it is for some of the other, like the LSTM or bi-LSTM. The idea with ELMO is for you to be able to actually represent a single word in context very well. And so the forward and backward kind of work together to make that word vector reflect its forward and backward context of its whole sentence. Okay, so that's what Elmo was trying to do. But people often, so Elmo is more specifically for contextualized word representations. Bi-LSTMs are often used for a lot of different things. So I'll leave bi-LSTMs here as a picture. Now, people took these language modeling ideas and, hey, we've got a sequence of things happening, and we're going to pass, we're looking at the words, but then people started to consider using just a different mechanism, the attention mechanism. And so attention became fairly popular, and it was being incorporated into a lot of things. For example, you can include attention up here at the top layer here where you're predicting these classes. You can include attention in a lot of places in a lot of these different deep learning strategies. But a sort of landmark paper called Attention is All You Need introduced what's called the transformer unit. So instead of these LSTM RNN type units, the transformer unit is just an attention-based unit. These are actually directional in the LSTM, the RNNs. They're directional. You're passing information forward, whereas these attention mechanism, this is not really so directional. It does require a ton of training data. And OpenAI GPT, these were the first guys with these forward links to use the transformer in basically modeling language. And so they modeled huge amounts of language with this model, and it dethrones the previous language modeling strategy in a lot of competitions or in a competition and stuff like that. But then I think only a few months later, it was upstaged by BERT, bidirectional encoders from encoder representations from transformers. So obviously you can see that NLP people are kind of nerds. They were riffing off Elmo, and now they're making BERT's Sesame Street theme here. And so BERT was basically had the extra links going backwards that OpenAI GPT did not. And the thing about BERT is that it's probably the most popular strategy for language modeling right now. It's not just for language modeling, because what's happened is that BERT models are pre-trained on a huge amount of data, and they actually model language pretty well, and they can be fine-tuned for a lot of other natural language processing tasks after the fact. Like you pre-train on and you have the pre-trained BERT model, and then you fine-tune your task to the specific thing that you want to get out of your natural language processing. So a lot of people are using BERT nowadays. After the fact, actually, interestingly, OpenAI GPT sort of re-released as a 2.0 without really changing their model. But what they basically said was, hey, we can run this one that had only the forward links. We can run that one as a generation kind of tool. And so they can generate lots of very coherent, at least computer-generated texts that seems almost believable, almost human, or maybe even sometimes basically similar to humans. So interesting that each model kind of has its unique points. So speaking of generation and those kinds of models, there are a bunch of other models of generation. One of them, for example, here is the sequence-to-sequence model, or seq-to-seq. And so if you took your LSTM from over here and you just, when you were doing the training, you said, hey, I'm going to give you a bunch of input, and then I'm going to give you an end sequence, and then I'm going to tell you a new sequence that you're supposed to have predicted. Then that would be kind of the setting, for example, for translation. So here you give it the input of one language, and then you give it an end sequence, and now it has everything it needs to know about that whole sentence up to this point, and now it's supposed to predict the sentence in the next language. So this is another deep learning architecture for the natural language processing task of translation or of generation, depending on how you want to run this kind of model. So there it is, a whole bunch of 5 different, or 5+ different architectures of deep learning for natural language processing. Now that we've looked at that, we still want to ask the question, how is deep learning being used in clinical natural language processing? Well, to answer that question, we performed a methodical, or we wanted it to be a systematic review of deep learning in clinical natural language processing. And a team of us, 12 of us here at UTHealth, Hua's group, we basically wrote an article about our findings. It's in press at JAMIA, and you guys are going to be the first to hear about it. So it was just accepted a couple weeks ago. So basically, what we did was a systematic review. And if you're not familiar with review papers, it kind of goes like this. You look in databases and other places for a bunch of articles, and we did this according to, as close as we could, to Prisma guidelines. We searched on April 10th, 2019, and after you get back all of those articles from different sources, you eliminate duplicates, and then you look through the titles and abstracts for whether things actually fit into your study or not. And so we were looking for, the search terms are not always precise, etc. So we were looking for things that are deep learning and NLP, and being done in a clinical setting, and specifically EHRs, electronic health records. And so we did review by 12 co-authors through title and abstract to find whether these articles fit the bill. We looked at 250 of them full text and excluded 38 more of them, so that at the end we had an included data collection of 212 articles. On those 212 articles, we got 25 variables worth of data. We had a survey that we basically answered 25 questions on for each of these 212 papers. So it's a lot of work, but it gives us a big picture view of everything that's being done in deep learning methods in clinical natural language processing. Now, what we're trying to do here was answer 3 research questions based on the data. Number 1 was a methods question. What deep learning methods are being contributed or applied in the literature? The second research question was of scope. What types of problems are addressed and solved in the literature? And the third research question was one of context. How do these articles fit into the wider research context? And we mean that pretty generally. Research context in terms of the emphasis on scientific rigor, preprints, prevalence of preprints these days, and other stuff like that. So context pretty generally, but these are 3 questions that we tried to answer with the data. So this is a very active area of research, deep learning in any kind of computational field, but deep learning in NLP and clinical NLP even more specifically. There's plenty being written about it. That's how we have 212 papers. But it's an active area of research. It's also an active area of summarization. You can see all of these articles here on the right side of the screen are other review articles in a similar or related field. And so it's pretty active in terms of an area, but not every one of these studies is exactly the same. The ones that are bolded here, Dreisbach et al., Wang et al., and Xiao et al., these are the ones that are closest to our study. But our study is distinctive in that it talks about deep learning, it talks about actual NLP, and we're not just NLP methods, and we're focusing on electronic health records. There's, for example, this Dreisbach et al., which is similar. It has patient-authored text instead of clinician-authored texts. So electronic health records, that was another limiting factor. We basically tried to follow the PRISMA guidelines on review. So, for example, this Schickel et al., they did something very methodical, but it was not according to PRISMA guidelines. Then we also did a lot of quantitative analysis, and you'll see that analysis in a lot of charts and tables and stuff that I'm going to show you, which is not always common in other review papers. So let's look at the results of our literature, looking at the literature through this methodical review. What are the deep learning methods that are being contributed or applied? So first, let's look at the deep learning architectures. I gave you that huge map of different deep learning architectures, but when we look at the actual data, we had to sort of group together some of these in order to see trends and to see anything meaningful out of it. So we had 5 different categories, RNNs included, long short-term memory, LSTMs, as well as gated recurrent units and stuff like that. CNNs included lots of variants of CNNs. And so what you see here in these 5 is that if you look at the relative groupings, RNNs are the largest grouping, and they account for a large percentage. You can sort of see all of these green ones together. They account for the most of the sort of architecture classes here. CNNs are number 2 in the frequency. They're the orange bars here. It's interesting that you even find, no matter across the board, that the number of deep learning, papers was increasing each year. This 2019 was a dip because we only went up through April 10th, 2019, and so you fully expect it to be much higher in the end, so that it is also increased in volume. So basically, deep learning methods are growing, but the interesting thing about this is that even feed-forward neural networks are growing. So you see feed-forward neural networks, which aren't really deep learning architectures. It's the same old multilayer perceptron that we learned about before, maybe with some improved optimization techniques and whatever else. But it's the old school things being sort of, their boat is rising along with the rest of deep learning. Yes. So that was kind of interesting. Another thing to point out is this attention line. We've included it here as a line where this is 0% over here. And we're basically saying how much of these techniques used attention. And since attention most of the time floated for most of the history in this time frame, attention techniques floated sort of on top of one of these other techniques. You could put it on an RNN or a CNN at the last stage or somewhere else. So attention mechanisms, they were also increasing in their usage, but it didn't penetrate through like all of the deep learning techniques that were being used. We actually do expect that the use of attention mechanisms will increase drastically, and that is because of BERT. People are going to be using BERT as a pre-trained model, and that is based on the transformer, which is an attention mechanism. Now, if we look at not just the deep learning kind of methods with the full nonlinearity and all that other stuff, but you look just at the embedding techniques, what you can see is that word2vec is the most common embedding method. You can see word2vec only is here, but word2vec combined with other things, and then word2vec compared to other strategies, these accounted for 74.1% of all of the papers. So a huge proportion used word2vec. However, many people found it necessary, many papers found it necessary to augment with subword models, like going down to the character level or looking at positions, or there's also some subword models for the glove word embeddings, a different word embedding technique based on matrix factorization. Fast text is also a subword model, so there were plenty of folks who felt like they needed to have that subword level of model. Besides these kind of more normal embedding methods, there were less common embeddings, and there's a bunch of them listed in the paper, and you can see them here. They were used on a bunch of different tasks, and I'll just say also that sometimes you had integrated methods where you're learning a whole language model, and therefore your embedding is your word embedding or whatever is actually learned alongside at the same time as the other model. Okay, so these are some of the embedding methods that are being used. Now, in the methods, if you've been doing clinical natural language processing for any length of time, you know that, or if you're in the field, you know that there's actually a lot of medical terminology resources. There's SNOMED CT, there's UMLS Meta Thesaurus, there's the NCI Thesaurus, there's lots of medical knowledge out there where people are spending lots of effort to curate medical knowledge. So did a lot of people use medical knowledge? And the answer is really no. Only 17.9% of the papers on deep learning in clinical natural language processing used any kind of external knowledge, or at least reported doing so. And so you had a few of those using a custom lexicon or an existing non-standard lexicon. But then you also had people using the UMLS, was the most common, where by UMLS we mean UMLS Meta Thesaurus. And then ICD codes were also used. And SNOMED was also used fairly frequently. Now, only 5.7% of all of the papers incorporated knowledge into the deep learning architecture. So you could use external knowledge in the paper without even incorporating it into the architecture. A few of them incorporated it, but most of them incorporated it by basically just creating knowledge resources embeddings. For example, getting embeddings for a concept, and that was 11 of the 12 papers that incorporated the knowledge into the deep learning architecture. So there's only one example of someone who used a knowledge resource embedding that wasn't just that they actually had to change the architecture due to the knowledge resource. And you can read our paper to find out which one that is. So Another thing to think about in terms of the methods that were being used is how did people actually implement um, the work that they did in these deep learning algorithms. And so most of the papers did not report this kind of thing. And what you see here is the the six most common papers. I'm sorry, deep learning libraries. So obviously, people are not coding deep learning algorithms from scratch these days. You have TensorFlow, which is Google's toolkit, that is the most common. Keras is this the one that I use, and it's kind of a layer that sits on top of either TensorFlow or Theano, and allows you to define some of the typical things that you want to do a little more friendly in a more friendly way so that you can play around with architectures a little more easily. Um, and then there's a few others. This is the Deep Learning 4J is the Java specific one. And you can see that these papers, the ones that did report at least which deep learning library they used, they basically reflected what is being done outside. Okay, actually, I don't have that plot here, but basically it reflects what is being done on the outside of clinical natural language processing. It reflects the trends of which packages are being used by the general computing community. You can see that TensorFlow is very popular, Keras is very popular, and Deep Learning 4J has dropped off in popularity. Theano has enjoyed some increase, but not as much as TensorFlow. I don't even know how to say Lausanne. I have never used it, and it is kind of decreasing in popularity a little bit. So anyhow, if you're interested in deep learning or natural language processing, feel free to look at these slides and follow the links here to these packages. There are also natural language processing packages that are being used, and you might be able to find the links for those in the slides as well. Okay, so that gives us a little bit of an idea what the methods are that are being used in deep learning and natural language processing. Now we'd like to see what types of problems are being addressed and solved. So this is our second research question on scope. What types of problems are being addressed and solved? Well, the NLP tasks that are being addressed here in the 212 papers that we reviewed, we again had to group things together, so just to make sense of things. But we have an overarching category called text classification here, which has a lot of diverse things in it. The most common thing here was phenotyping. If you're not familiar with phenotyping, you're basically looking for how people experience health and looking at it at a very large scale. So you're doing a sort of agnostic gathering, extraction of information at a large scale for a lot of patients and looking at their health characteristics at a large scale. So we considered that, and for example, mortality prediction, life expectancy prediction to be kind of like a classification problem. You're taking some text and you're trying to predict some class from it. So it's not a perfect fit for all of those things. This is a loose gathering of things. Named entity recognition is a little bit more focused. It's mostly clinical concept extraction here. 61 papers on that. We had some papers on relation extraction, and then we had a long tail of other kinds of natural language processing related tasks that were being done. Now, if we look at these tasks, these are the groupings that you just saw: text classification, named entity recognition, relation extraction, and others. And we actually plotted, well, what types of architectures are being used for each of these. So what we see here is we're confirming our assumptions that that convolutional neural networks are oftentimes used for text classification. This green one is a convolutional neural networks, and it's being used for text classification the most. Named entity recognition is typically done with RNNs, more specifically with LSTMs and GRUs, not really vanilla RNNs. So that's kind of a bias because you can do NER, you can do named entity recognition as a sequence prediction task where you're predicting the label of words on a sequence. And that's a really good fit for the RNN model. We actually expect that we'll see perhaps more of the transformer and BERT and stuff like that in named entity recognition tasks in the future as well. But it wasn't visible in the data that we had up till April 10th this year. Besides that, when we're thinking about the scope of what's in these papers, where did the corpora come from? And this is kind of an interesting question of scope because it also it touches on who can participate in this kind of research. So where did the labeled corpus come from? And what we found was that almost half of the papers used an institutional data set or a proprietary data set. So basically one that is not available to anybody else. So that's interesting. But besides that, the next large grouping is data sets that came from challenges, like the I2B2 challenges, also the N2C2, we kind of grouped that in with I2B2 challenges, NLP challenges. There's a number of other challenges, and these machine learning challenge, NLP challenges, have really produced a lot of good data sets, and they have been sort of celebrated by the community. Now, some of these challenges actually used the public data from these papers, from these data sets. However, the public data sets here that we're talking about actually were not participants in these challenges and yet use the same data. So you can see that some of these counts maybe would be higher. More of these would be using mimic data, for example, if you included the ones that were from the challenge. But we wanted to keep those separate because oftentimes the mechanism for getting challenge data and the mechanism for getting public data are a little bit different. So now when we're looking at the corpora, the language of the corpora is an area that we found a little bit of surprising information. The English language is definitely the most well-resourced corpus here, or type of language of corpus here, but Chinese language is far and above the number 2, far above the following languages after that. So for deep learning in clinical natural language processing, lots of Chinese corpora and tasks and methods as well, working on Chinese. And we found that to be a little bit surprising because we had read a recent review paper where you looked at clinical natural language processing in languages other than English, and Chinese was, not one of the top languages. It was actually ranked number 5 in terms of the number of articles from that language. Of course, this article, RLE's article, is not exactly comparable to our study. The time frame was different. It was before there was a ton of deep learning. There was some, but not nearly as much as there is today. And ours is focused on deep learning. So these are not directly comparable, but at least you can see that whereas the Chinese did not used to be as important perhaps in traditional clinical NLP. When you're talking about deep learning in NLP, clinical NLP these days, it is a clear second. And in fact, that it was actually the case since the beginning of deep learning popularization. We actually crossed this stuff here with the year that it came from, and this is a little bit more raw of a table, but you can see English language started picking up in 2016, and if you look at English and Chinese here, it started picking up in 2016 as well. And if you look at any other language, Finnish had 2 here in 2015, but then went down. But besides that, Chinese has basically, since the beginning and continuing till today, been a clear number 2 in the languages for deep learning and natural language clinical natural language processing. So that's an interesting note on the multilingual scope of this kind of work. Now, the contributions to science that were presented in our 212 papers, we have categorized them and put them into this sort of block diagram. And here the area within each block kind of tells you that is representative of the number. So the number and the area here are telling you the same thing, basically. But in terms of the contributions to science, we broke it down as applications versus variants of existing deep learning techniques, and then new deep learning architectures or NLP tasks or embeddings. So these are newer things. Then papers talking about resources for NLP, and papers that were evaluating different methods. And so what we did in terms of contributions to science was, hey, let's set a low bar for novelty. Okay, if they're just trying to present a new deep learning architecture, not just a variant of an existing one where you just change some parameters or something, but you're trying to present a new architecture, whether it's really that novel or not. We didn't try to judge. If you're trying to do it, then we counted it. If you're trying to create a new NLP task, or if you're trying to come up with a new, we're embedding this kind of things instead of just words, then that's a low bar for novelty. But it only accounted for 20.8% of the papers that we reviewed, and this was the slowest growing contribution type. 2017 to 2018, it only grew from 10 to 17 papers. So in terms of the percentages of the overall types of contributions in each year, it seems like maybe there are fewer and fewer really more novel types of papers from a methodology standpoint. The methods variants, now these are the fastest growing type of paper, and you take one type of deep learning algorithm, you tweak it a little bit to match your data set and your specific task, and maybe make a few variations. That's the fastest growing type. Okay, so people are making different types of contributions to science. Now, our next question to answer here, our next research questions, our last one is, how do these articles fit into the wider research context? How do these 212 articles, how do they fit into the wider research context? Or more generally, how does deep learning and clinical natural language processing, these types of articles, how do they fit in? So we wanted to look in the research context at, well, what about the different communities that could contribute to deep learning and NLP, clinical NLP? And so we split the communities, the venues in which things could be published, into 5 different communities. So informatics would be like AMIA, JAMIA, JBI. CS would be like NeurIPS, stuff like that, some ACM stuff. NLP would be like ACL, all of the ACL conferences, NACL, the workshops, LUHI, and BioNLP, stuff like that. Medical, these are like typically medical journals, um, straight medical journals, and then other types of uh, publication venues. So what you see here is that NLP, if you look at when this started taking off in each of these communities, you can see that NLP was sort of the early adopter in terms of deep learning in clinical natural language processing, where you saw most of the clinical stuff happening was in the NLP community in 2016. But soon afterwards, both the CS community and the informatics community jumped on board. And a little bit later, you see the medical community start to get involved and is slowly getting involved. But this is an encouraging trend that whereas in the past the medical people were viewed as people who would not be happy with the black box of a neural network doing their work for them when they definitely know better. This is what people thought clinicians would the way that they would respond, but actually there is some traction being had in the medical field as well. Another interesting point here, we did split up between conferences and journals, and you can see how computer science and natural language processing communities really publish everything in conferences, whereas medical publishes everything in journals, and informatics is kind of a blend of the two. So that was kind of fun to see as well. In the research contexts of today, we see that there are a lot of preprints. There's the archive and there's bioarchive. And so a lot of people have been saying things like the most cutting edge, bleeding edge research is on archive. And so you really need to check that out. And so we did. We looked at our 212 papers. Were they posted on archive before? And actually, although the number of papers that were being posted on archive was increasing from year to year, 35 out of 212 is not at all dominant. It's most of the papers that met our criteria were actually were not first published on archive. So that's interesting. Perhaps it's reflective of the fact that we're in a medical domain where I think people, the research establishment tends to be a little more controlling of whether the publications are seen before they are accepted by a journal. So that's interesting that we're kind of saying, no, you don't actually need to put everything on preprints. Not everybody, at least not everybody else does. And second point here is one regarding scientific rigor. There's a lot of emphasis on replicability and reproducibility of results, and we didn't do a study. This is not a replicability study or a reproduction study, and we didn't actually try to reproduce results of anybody. But we just wanted to say, well, did people leave enough details, enough resources, so that if someone was going to do a replicability study, they might be able to do it. So we looked at this in two different areas. One, did people provide actual software that you could take and run? And if they did, wow, you're golden, that's great. But sometimes that might be restricted. That might be a commercial license or something like that. It might be proprietary software. If it's open source, even better. Or if it's open source, that's better. But either way, the software, if it's made available, we showed that here. The other question was, well, sometimes you don't need to download software if you just are able to set the hyperparameters and use the public package the way that that they used it, and you just set the hyperparameters, then you can run it and get the same results. So did they report those hyperparameters? And so maybe they didn't provide it, maybe they gave some hyperparameters, or maybe they gave everything that they needed to give. It's present there. And so what we see here is we kind of get a picture of what percentage of papers is providing sort of hooks for you to be able to do replicability studies in the future. And most people do not provide software, but an encouraging number do provide hyperparameters. If you put these and these, if you put these and these together, then you get like 66.38% gave some kind of resource corresponding to rigor for the future replication studies that could be done. Okay, I think this is our last one, and so we want to kind of ask here, are people comparing with traditional machine learning? And if yes, which one was better? Okay, are people doing the comparison with traditional machine learning? Because deep learning is kind of all the rage. And so what we're seeing is a decreasing percentage of papers are comparing with traditional machine learning strategies. These gray bars are the ones that have no comparison of the deep learning algorithm with a non-deep learning traditional machine learning comparison. And so this percentage is growing. You see it here, 30% to 37 to 45. Partway through 2019 it was at 53%. And so a lot of people are starting to say, well, the baseline that I want to compare with is just another deep learning baseline, so I don't need to compare with traditional machine learning. That's interesting. We think it may be a little bit dangerous, but that is the trend that's happening. And on the second question, if they were comparing with traditional machine learning, so that's everything besides the gray bars here, then mostly deep learning had better performance. That's these green bars. So 72% of this non-gray bar shows that deep learning has had better performance. But there are some negative results, and negative results would be these purplish bars, where the traditional machine learning actually beat out the deep learning algorithms. So yes, deep learning is empirically shown to be very, very effective, but that does not guarantee that it's going to perform well on every single task, every single time. Okay, so what can we say summing up some of the stuff that we saw? Well, we can say that acceptance of deep learning is growing, and that's it, both in terms of using it as a baseline as well as the clinical community is even accepting some deep learning applications. We saw a few substantiated results versus surprising results. Things like, oh yeah, we do use CNNs for classification, text classification, most of the time. Oh yeah, we do use LSTMs for NER most of the time. Whereas there were some surprising results about French versus Chinese, as the fact that Chinese was a really strong second language in the data. That was kind of surprising. Yeah, so here's some of the substantiated things. Another surprising thing was that there were few knowledge resources used in any of these deep learning strategies. And perhaps it shouldn't be surprising, because the whole idea with deep learning is that you don't have to manually code your features. But it was a little bit surprising in any case, because most of the work in clinical natural language processing before this, or much of the work, actually did include knowledge resources. So people have dispensed with that. We think that this could be an area of growth to look into those knowledge resources. So we have a few projections. We think that domain adaptation and transfer learning with deep learning is going to be an area of growth where people are learning how to do domain adaptation and transfer learning well, especially with the advent of BERT, where you can pre-train a model and then you're fine-tuning, you're adapting to different domains. We think that this is kind of a frontier that will need to be uh, solved to get into the many different silos of medical data that are available or unavailable. Um, so a second projection is that we think medical knowledge, again, will become more important to guide the deep learning algorithms. People have been talking about inductive bias, and basically the deep learning algorithm is going to learn whatever you provide to it in terms of its data. And so medical knowledge will be used to guide the inductive bias of deep learning. We think that analysis, or we actually would like to see more analysis of the limitations and failures of deep learning in these clinical settings. We think that there will be fewer truly novel core deep learning methodologies. We think that BERT is getting pretty close to something that a lot of people are going to just take and apply and find other kinds of ways to build on top of that. And so the so truly novel core deep learning methodologies probably are they're already kind of infrequent in this domain deal in clinical NLP, but we think that will also still not increase that much, or maybe even decrease. Finally, we see that there will probably be lots more application and tweaking of deep learning algorithms for a long time to come. We think deep learning will continue to be with us and will continue to be used and will continue to be fine-tuned well for lots of different end tasks in the clinical domain. So as an overall conclusion for this whole lecture, we have looked at deep learning as a phenomenon. We looked at some neural network basics, and we looked then at the deep learning architectures in natural language processing. You saw a huge map of pictorially what some of these architectures look like. And then we looked at the literature on deep learning in clinical natural language processing and concluded that it's a hot field, lots of stuff is happening, and at times it's happening in areas different than we expected, but it seems to point to still a promising future. All right, thank you everyone for your attention and for listening on deep learning in clinical natural language processing. Feel free to get in touch with me at one of my emails or website, or connect with me on LinkedIn. Have a good day. God bless.